Welcome to the third and last video in my little series regarding problem-solving recipe. Uh, have you gotten to a point in your class where you quickly read a problem and you panic maybe a little bit and you say, I don't know how to start, or I don't know where to start? That is always possible. A number of folks get through the first couple of chapters and they're feeling pretty good. They might get to the third chapter and have those feelings of, man, I don't know how to start this problem. What I want to do is give you a worked out problem for a problem that could be considered a little complex. Um, the problems do get harder, but what I want to do is show the recipe that I'm recommending might help you get over that initial panic or give you some ideas on where or how to start. So let's go ahead and get started. Okay, like I say, it's the third video on our problem-solving recipe that I recommend you consider adopting for yourself. At a minimum, think about what works best for you. And you might decide to adopt all of this. You might decide to modify it a little bit. You might decide to add some things to it. So what is that recipe? One is read the problem in words, start looking for clues and cues and what's wanted in the problem. The next thing you do is you start with a sketch. You immediately draw a sketch based on your understanding of the problem. Once you've drawn that sketch, you're going to plan your work in your mind. And then finally, you'll work through the solutions. That putting pencil to paper or however you're solving your problem, you're going to work down the page. It helps keep you straight. It helps the person reviewing your work understand what you're doing better. You're going to write down fundamental equation or equations that apply to the problem at hand. You're going to show and explain your work. Maybe it doesn't have to be sentences or paragraphs, just maybe a few words here and there. You're going to use units throughout your solution because units are just as important as the values that you're driving towards. And you're going to explain your work in words or some very short phrases, again, to let the person reviewing your work know that you know what you're doing, but also when you're going back and reviewing your own work a few weeks later, when you're preparing for a quiz or a test, it'll remind you what you were doing in solving the problem. Okay, so here's the problem that I'd like to work out, and it is representative of a real problem that we would have early in chapter 3. And so here's the problem. A rigid vessel propane tank for a gas grill. And here's that propane tank. Here's a grill that looks a lot like my own gas grill. That the propane tank has a volume of 0.64 cubic feet. It says the tank is partially full of saturated liquid propane and the remainder is saturated vapor propane. The mass of the saturated mixture is 10 pounds mass. It says the initial temperature of the contents in that propane tank is 70 degrees F, sitting in the garage. And the tank is left out in the hot sun until the contents of that tank reach a final temperature of 100 degrees F. Determine the initial pressure and quality of the propane in the tank, and determine the final pressure and quality of the propane in the tank. Okay, a lot of words. So let's go back and read the problem for clues and what's wanted, that type of thing. Let's see, let's jump down to what's wanted first. So determine the initial pressure and quality of the propane in the tank and the final pressure and quality of the propane in the tank. Wow. So what does that mean? We're looking for 4 things. What's desired? P1, that's the initial pressure. X1, that's the initial quality. And final P2, final pressure, and X2, final quantities. So we're looking for 4 things. Wow. So that's going to be a study in something other than one equation and one unknown, isn't it? So it's probably going to be a set of things to work on. Hopefully we can work on one thing at a time and blast through this problem. Okay, now for keywords. Okay, a rigid vessel and tank. So those words tell me that what we're looking at is a closed system. So that's going to be important. Let's see, another propane. So mentions propane a number of times in the problem. So you should recognize the word propane, C3H8. Commonly, we recognize propane as a substance. It's a fuel, but it changes phases, right? So common sense tells you we use propane for a gas grill. Gosh, it says it right there, gas. But you know that liquid propane is stored in that tank. So commonly, we're going to recognize propane as a phase change substance. And so immediately we're going to start thinking about the property tables in the back of the book. All right. What else is given? The mass of the propane mixture is given. Oh, and wow, this one really important. It says partially full of saturated liquid. Very important clue there. Partially full of saturated liquid. And then it goes on to say, it says the remainder is saturated vapor. So right there, that's screaming out that this closed system is a 2-phase saturated mixture. So inside that tank is going to be some amount of saturated liquid and some amount of saturated vapor. So that's an important clue there. Okay. Also disclosed is the initial and final temperatures. Those are given. T1 and T2, that's given. And what we're looking for is initial and final pressure. How are we going to get that? Okay. And then quality, we're going to have to refresh our memory on what does quality mean. I hope that you remember that the definition of quality, it's for a substance that is in the saturated 2-phase mixture phase, that the quality is the mass of the vapor divided by the total mass. Mass of the vapor divided by total mass. That's what quality is. Okay, so now we've dissected the problem, we've looked for what's wanted, we've got our clues. Next step, start with a sketch. Don't start solving the problem, start with a sketch. Your sketch does not need to be a work of art like this is, okay? Hand-drawn is going to work fine, but what would you have in common? One is I would write down the words closed system. That's going to get me something. Here in my sketch, I'm showing a rigid vessel, clearly showing not a piston and cylinder. It's a rigid vessel of a fixed volume. And my little dashed line inside the rigid vessel, that's depicting the closed system of propane, C3H8. What else am I doing in my sketch? I've shown a little dashed level line where down below, because of gravity, I've got saturated liquid, and up above this level line, I've got saturated vapor. So do you see that on my sketch, I'm depicting that I have a saturated mixture? That's helping me see, reminding me that I've got a saturated mixture. Let's see, I've written down the given information, T1 and T2, 70 and 100 degrees F. I am showing, for this problem, I'm showing a big arrow going in of heat added. That's what's helping me to explain that my temperature's going up. Temperature's going up because I'm adding heat. Another thing I did was I wrote down the given information, the mass of 10 pounds mass, and the volume, given volume of 0.64 cubic feet. And that helped me, that reminded me, oh, specific volume. I bet specific volume is going to help me solve the problem. And the definition of specific volume is the volume over the mass. And so I wrote down little v is capital V over M equals, and for this problem, it's a constant. It's a rigid vessel. The volume is constant. It's a closed system. Mass is constant. So therefore, specific volume is constant. And so I wrote down little v1 equals little v2. Little v1, that's critical, okay? In some ways, that's like a fundamental equation just about for this problem. Certainly a fundamental definition is little v equals capital V over M. So that would be really important to write down on your sketch. Okay, so a lot of information in that sketch. Now I'm going to say that I'm going to continue my sketching, looking ahead a little bit. I've got a phase change substance. Typically, you immediately, for a closed system, you will immediately think, I'd better draw down a pressure-specific volume diagram just for the heck of it with the vapor dome on it. I'm just going to draw that down with the vapor dome on it and then try to draw the process involved. So let's do that. Now, if I was doing pencil and paper, I would probably draw my PV diagram off to the right. But just for PowerPoint and all, I'm going to go to the next slide. So how do I do this? First thing, draw my axes, my y-axis, pressure, x-axis, specific volume, and label it P and little v. Next thing I do is draw my vapor dome. Draw a vapor dome. Okay. And remind myself, I should know in my head, oh, this region over here, that's superheated vapor. This region below the dome, that's a saturated mixture, vapor and liquid mixture. That's what we've got. That's our problem at hand. Over here, this is compressed liquid. So where are we living? So that once I've got my dome, I'm going to draw in my states. Well, the first thing I do when I'm solving a problem is I'm going to draw in a line of constant temperature, really just about anywhere. And I'm going to say that's my initial temperature. I'll label it 70 degrees F. That's a line of constant temperature. And then I think, okay, where's my initial state, state 1? It's given in the problem that is a saturated mixture. So I'm going to plop down 0.1 anywhere under the dome. So it can be anywhere. Just plop it down anywhere. So I did. All right. So and I'll label that 0.1. Next thing, well, where would 0.2 be? 0.2. It's on my rigid vessel diagram. I've already written down that little v1 equals little v2. So I know that state 2 has got to be on this vertical line somewhere, and it's going to be at a higher temperature. And so I remember from my classroom lecture that if I draw in another line of constant temperature, at a higher temperature, it's got to be above the lower temperature. So I draw in another line of constant temperature. That's called an isotherm. Okay, isotherm. And I'm going to label it 100 degrees F. And so I'll draw a little vertical line. And so immediately, boom, there's state 2 right there. So I'll put a dot there, and then I will depict my process 1 to 2 as this arrow, vertical line with an arrow 1 to 2. And that's pretty much it. Now, another thing I've done on my sketch for this presentation is as a reminder, what's this dot right here? What does this dot right here represent? It represents G. That represents saturated vapor. That's when the mixture is totally vapor and no liquid. And what's this dot over here? That's F. That's for saturated liquid. F for fluid. But anyway, that's typically, we call F, that's saturated liquid. That's where we are in saturated liquid. So that's just a little bit. And I think if I were solving this problem by hand, I'd probably put F and G there on my sketch as well. So there's our pressure volume diagram. And it just kind of came to me to talk a little bit of details of big deal. This whole finished product is a PV diagram. But that's how you would create the PV diagram from scratch with pencil and paper. Draw your axes, draw your dome, draw a line of constant temperature. That's an isotherm. Locate your point on the graph, and then apply what you've learned from the words of the problem. That's the rest of it. Let's plan our work. We're looking for 4 things: initial pressure, initial quality; final pressure, final quality. All right. Let's plan. What do we know? We know it's a closed system. The mass is constant. We know it's a phase change substance, propane, a rigid tank. So we've already shown on our sketch. Our sketch is helping us plan. The sketch inspired us to realize that little v equals constant. Okay. Okay. And so since v is v over m, then v1 equals v2, and it's going to be easy to determine. The specific volume is going to be easy to determine. And so the phase is a saturated mixture. And so those words were given in the problem. That's what enabled us to draw our sketch. So this is a little bit like a chicken and egg type thing, isn't it? So the phase, saturated mixture, that's what enabled us to draw our sketch. Let's work on state 1 first. Well, we've drawn our sketch. Well, T1 is known, and the phase is saturated mixture. So we remember from our classroom lectures that under the dome, if you know the temperature, the pressure is a dependent variable. So you can use your temperature table in the back of the book to look up the saturation pressure at that temperature. That's a little bit like the boiling point. So remember that for any phase change substance, there's a very special, at any pressure, there's a certain boiling point temperature. So if you think of the converse, at any temperature, there's a certain saturation pressure associated with that boiling point. So we're going to use our temperature table simply to determine P sub G at state 1. That's going to be P1. Okay. Now, another thing we're going to do when we're looking at the table, we're going to write down VF and VG because I think we know V. So I didn't put, darn it, I didn't put it up in my planning. Look, we know V and we know M. So little v is going to be V over M. So somewhere, here we go. So I think, I guess I did. We're going to calculate the specific volume V1 using V over M. There it is. Okay. So we've got V. We will write down VG and VF. Then we will remember the definition of quality. The definition of quality, let's see, it's the mass of vapor divided by the total mass. You can derive this, that the quality is simply V minus V1. I've got a, darn it. It's V minus V1 minus VF. This is another typo, darn it. Hopefully I'll fix this in my solution. X1 is going to be V1 minus VF divided by VG minus VF. Let's go back and look at that PV diagram to explain my typo blunder here. So I'm sorry about that. Look at the terrible typo blunder. Let's go back and look at the PV diagram. Here we go. Quality, definition of quality. Quality is like a ratio of things. It's a ratio of, imagine this distance, V1 minus VF, so I'm saying it right, even though I didn't write it right, the quantity V1 minus VF divided by this distance, VG minus VF, okay? So visually, I'm correcting my dumb typing error, okay? Numerator, V1 minus VF. Denominator, VG minus VF. There it is. Okay, there's my typing blunder. Well, sorry about that. Anyway, we just answered two things. We're gonna find P2 using a lookup. We're gonna write down VG and VF, and then based on the definition of quality, we'll numerically determine X1. So we've got P1 and X1, and then it says same drill for state 2, except we're going to use the T2, 100 degrees F, for our lookups there. Now, let's go and do the work. So this was simply the planning phase. Planning. Okay. Woo, so I think we got a good plan. Let's determine the specific volume first. V1 equals V2 equals V over M. I solved my work with Excel, so my yellow cell is something I fat fingered in. 0.64. And I didn't just type out 0.64. I said what it is, tank volume, capital V, in cubic feet. So I've got units in my solution. 10, it's not just 10, it's 10. That's the mass in pounds mass. So therefore, the specific volume is V over M, 0.064, and I've got units of cubic feet per pound. I'm going to continue to work down the page. I've got to go to the back of the book or electronically bring up this table for propane, saturated propane, liquid vapor. That's what we've got. I'm going to come down. And so using the temperature table, because that's what I've given, the temperature, look down the left column. Here's 70 degrees F. All I have to do is look with my eyes, 124.9, and put that in my solution. I write it down. 124.9 is P1. And I'm in my work, I say, well, that's just PG at T1. PG, that's the saturation pressure. Okay, so there's an answer, 25% of the way there. Looking ahead, I'm going to write down VF and VG at state 1. So I call it VF1 and VG1. Here they are. Just look at the numbers, write them down. VF 0.03213 cubic feet per pound, VG 0.8593 cubic feet per pound. And just as a check in my work, here's our specific volume that we determined. Is it between these two numbers? Yes, it's bigger than 0.03 and less than 0.86. So this is, we just verified we've got a saturated mixture. Okay, we're really getting there now. Next step, we remember the definition of quality. So here's my three blue cells, because we've already mentioned that up higher in our work. And again, just for the slides, moving down the slides, that's why I've got blue cells. And whoo, I fixed my dumb typo from the PowerPoint here in Excel. I've got X1, that's the quality at state 1, is correctly V1 minus VF1 divided by quantity VG1 minus VF1. So we do the math. It is 0.038529. Way too many significant figures. So also I'm repeating, I can say, what's that in percentage? It's 3.85%. So what's the practical conclusion so far of our problem? It says the initial state of the propane is about 96% saturated liquid and about 4% saturated vapor. That's a good practical conclusion. So in that tank, in my gas grill, 96% liquid, 4% vapor by mass. Now we've got a good handle on this. All we got to do is repeat the drill for state 2, for the 100 degrees F, after the sun heated the contents of the tank. Go right back to the temperature table, same drill. I will come down to the left column, look for 100 degrees F and write down our pressure. PG at T2 is 188.6. We'll write down VF and VG. So let's do that carefully. VF is 0.03399. VG is 0.5605. Let's check just to verify. What's our specific volume? It's 0.064 cubic feet per pound. Is that in between these two numbers? Yes. So we verified, sure enough, we've still got a saturated mixture at the new hot state. Okay, that's great. We're 3/4 of the way there. We just got the pressure. It remains then to determine the quality at state 2. This is kind of plug and chug, very repetitious. And thank goodness I've got my, I fixed my typo from the PowerPoint. So the quality X2 is simply V2 minus VF2 numerator divided by quantity VG2 minus VF2 denominator to get X2, to get the significant figures to a reasonable number. X2 is, the quality at state 2 is 5.7%. So the practical conclusion, final state, about 94% liquid and 6% vapor by mass. Okay, and so you want to very clearly at the end of your solution, sort of show the end of your work, especially to the person grading your work. So the person doesn't have to go through all of the ins and outs. Person could drop to the bottom line. What's your bottom line? Makes sense to make a table, make a summary table. And so in the first column, I've got my temperature in degrees F. So that's from above. Okay. The pressure, we looked up two pressures. We found 125 PSI at 70 is the pressure in the tank, 189 PSI once it's been out in the sun and got up to 100 degrees F. Wow, that's kind of interesting. That look at how the pressure of the propane in the tank went up as a result of being out in the sun. It went up a lot. And the quality changed. The quality changed from 3.85% to 5.7%. And you've been able to do all of this without running a lab experiment, without doing stuff invasively to try to get inside your tank. So what did you learn from this? Okay. First thing you learned is for a phase change substance such as propane, if you can determine what the temperature of the contents is inside your tank, you can figure out what the pressure is without even a pressure gauge. I find that to be a very interesting engineering and practical result. So we determined that without hanging a pressure gauge on this vessel, we've got 125 pounds per square inch absolute inside the vessel. We also learned, of course, that the pressure goes up and dramatically when you heat the contents up. And of course, the third is that means there's a good reason why propane fuel tanks have a pressure relief valve on them. And that's a requirement by ASME pressure vessel code. And so I was able to find sort of this little sketch out on the internet. So this little hole over here, this should look familiar to those of you who have used gas grills with propane tank. There's this, of course, is what we hook our feed hose up to feed the grill. The other side of this fitting would be a little pressure relief valve and pressure relief orifice there that in case the propane tank gets too high of a pressure in there, there is a relief valve in this valve in order to release propane to the atmosphere so that you don't get an explosion of your propane tank. So anyway, I felt like this little example problem is a pretty good example of an early chapter 3 problem where folks who might say, man, I just don't know where to start. I'm hoping that the problem solving recipe helps you either see how to get started or where to get started. But I'm hoping that you will think about applying this approach, this problem solving recipe throughout this course and beyond. It's worked for me. So what is that recipe? We read the problem in words, looking for clues. What's wanted? What are the clues that help us understand how we proceed? The next thing we do is draw a sketch. Start with a sketch. For this problem, we drew two sketches. We drew the rigid vessel showing the saturated mixture in that vessel, and we also showed a pressure specific volume diagram with the vapor dome. Then we used the sketch to plan our work. That really worked out well. That's where I had that typo blunder, but I think we fixed it in the solution. We worked through solution, worked down the page, wrote down the fundamental equations. In this case, the fundamental equation was the definition of quality. We showed and explained the work, showed that units are as important as values. Okay? And then finally, we used some phrases and words, and of course, and we're always writing out units throughout the solution. And so that's just a recap of my proposed problem-solving recipe. Okay, I hope that helps. I hope that gives you some ideas, maybe get the wheels turning on how can I use a recipe, maybe a little bit, putting in some type of problem solving discipline in how you read and approach solving these thermo problems. I got to tell you that, folks, once you kind of get in gear, once you've drawn that sketch, and once you get into gear, that helps you keep moving. So many students have trouble getting into motion, knowing where to start. That can be a real barrier. So I hope I've given you some ideas on how to get started, where to start, and I do encourage you to use that recipe in your problem solving. So again, hope that helps, and hope you explore some more of my videos.